Hi folks, this is Heath. We're in a review session today for the first exam. Let's go ahead and get started. We've got a lot to cover. The exam will be this Wednesday. You can choose the location. You can start anytime between 9 and 7:30. The exam will be open from 9 a.m. to 9 p.m. But if you wait until 8:59 to start, you have 1 minute to complete the test because the test closes at 9 p.m. So your last starting time shouldn't be anything past 7:30, because after that you are just limiting the amount of time you have to finish. Once you start, you have 90 minutes to finish. Be sure to leave some time to scan your work. The test is 10 questions, and so you should be able to finish that up and still have time to scan your work. That's what I'm shooting for. You may use a non-programmable scientific calculator, like the chemistry calculator, but it doesn't have to be that specific model, but it has to be something that is functionally equivalent. You may bring in any notes you have written yourself. You can any practice problems you've worked through, any examples that you've taken down or notes that you've copied down from the videos, anything that you have written yourself, okay? But you are not allowed any other resources, calculator and notes that you've written yourself. All right? So good luck with this. So let's try a couple of these questions. Line L passes through the points 1, 0, 1 and 2, 4, 7. If line L can be described by this equation, find the value of C. So let's take this point 2, 4, 7 and substitute it in. So we get 2 minus 1 over A equals 4 minus 0 over 4 equals 7 minus 1 over C. Now this is a form of a line that we haven't covered, but we can do this calculation. This middle term, 4 minus 0 over 4, is equal to 1. And this is equal to 6 over C. And so C has to equal 6, regardless of whatever else is going on. So even if we don't recognize this equation, we can plug in a point and solve for C. Okay? This plane is described by ax plus 4y minus 3z equals 8. So its normal vector is 1, 4, negative 3. N is described by the equation ax plus y equals, ax plus y plus 2z is equal to 11. And so its normal vector is a1, 2. In order for these vectors to be perpendicular to each other, their normal vectors have to equal 0 also. So their dot product will be 0. And so 1 times A plus 4 minus 6 is equal to 0. And so A minus 2 equals 0, and so A equals 2. Okay? All right, let's move on. Let's talk about this surface here. If we rearrange terms, this is 3x squared plus y squared minus 2z squared is equal to 10. And we can divide through by 10 to put it in standard form. The importance here, though, is that we have a positive 1 on this side, not a negative 1. Dividing by 10 doesn't change any of the signs. All of the terms are present, all of the terms are squared, and there is one negative sign, and so this is a hyperboloid of one sheet. If you don't have access to the decision tree, or you can't remember decision tree, or it takes you a while to work through this, another way of thinking about this is look at the intercepts. We have intercepts on all three axes. And the x-axis, y equals 0 and z equals 0. And so 3 times x squared plus 0 squared equals 10 plus 0 squared, or 2 times 0 squared. And so x is equal to the square root of 10/3, plus or minus. And I don't know exactly what this number is, but that's okay. I just know that there's a positive and negative x-intercept. If I do y-axis, x equals 0 and z equals 0, that gives me y squared is equal to 10. And so y is equal to plus or minus the square root of 10. But if I look at the z-axis, I get 0 equals 10 plus 2z squared. And so negative 5 equals z squared. And so z is imaginary. And so I know that I'm looking at a shape that has an x-intercept on both sides and a y-intercept on both sides. But there are no z-intercepts. And so instead of curving inwards onto z, where we would cross over and cross over the z-axis, there is no place where we cross the z-axis. And so the curvature in the z direction, and we know there is curvature because it's squared and not linear. The curvature has to curve away from the z-axis. And that's what creates this hyperboloid shape. There is curvature, but it can't curve towards the axis because then it would cross the axis. And so it curves away from the axis instead. And that's your hyperboloid of one sheet. So if you didn't know the decision tree, you could plot the intercepts and know the curvature away from the z-axis is what's giving us this shape. Okay? Let's keep going. The trace of the surface x equals 2y minus 5z in the xz plane, and so y is equal to 0. Well, if y is equal to 0, this is x equals negative 5z squared. One of these variables is squared and one of them isn't. That's a parabola. It's like y equals x squared, but it's in the xz plane. And so the x-coordinate is based on the squared term of the z-coordinate, but it's negative. So it's actually curving in the negative x direction. Like so. Okay? Set the y-coordinate equal to 0. Recognize that with one of the terms squared and one of the terms not being squared, that traces a parabola. All right, let's try to evaluate this limit. If I try plugging in, I get negative 1 squared minus 1 squared. That's 1 minus 1 over negative 1 plus 1. That's undefined. And I'm writing under my picture here, but that's undefined. So plugging in isn't going to work. So what's some of the other things that we can try? This one yields to something fairly simple, the numerator factors. The limit as xy approaches negative 1, 1 of x minus y times x plus y over x plus y. These cancel, and we get the limit as xy approaches negative 1, 1 of x minus y, which is negative 1 minus 1, or negative 2. Okay. All right. Find the value of f of x sub x sub y at 0 pi over 2. This is a second partial derivative. So we need to find f sub x first. So we're going to take the derivative of this function with respect to x. And that derivative of sine of 2x plus y is cosine of 2x plus y times the derivative of what's inside the parentheses with respect to x, which is 2, because that's the derivative in the x direction. And now f sub x y is going to be the derivative of this, and the derivative of 2 cosine of something will be negative 2 sine of that thing, times the derivative of what's in the parentheses. But this time we want the derivative with respect to y. Well, with respect to y, the derivative is 1. So this is times 1, which doesn't change the answer, but I'll go ahead and write times 1 there. And at the point 0 pi over 2, we get negative 2 times the sine of 2 times 0 plus pi over 2, which is negative 2 times the sine of pi over 2. Sine of pi over 2 is 1, and so we get negative 2. All right. Let's keep going. For this equation, find the derivative of z with respect to y at the point 1, 0, 2. So we have a trick, and that's that the partial derivative is the negative reciprocal of the individual partial derivatives. So if I take the partial derivative of this whole thing with respect to y over the partial derivative of the whole thing with respect to z, change the sign, that's the same thing. The advantage of this is that I don't have to solve this for z. I don't have to figure out how to get the z by itself when it's in both of these terms. And this term is kind of complicated. And so capital F of x, y, z is what happens when we bring everything to the same side, x plus y plus z minus sine of x, y, z minus 3. The derivative with respect to y, x goes to 0, y goes to 1, z goes to 0. The derivative of negative sine is negative cosine. And then the derivative of the inside with respect to y is xz. The derivative with respect to z is 0, 0, 1. Derivative of sine is, again, negative cosine. But this time the derivative of the inside is xy. And so the partial derivative that we want, dz dy, is the negative of 1 minus cosine of xyz times xz over 1 minus the cosine of xyz times xy. And at the point 1, 0, 2, this is negative 1 minus the cosine. When we multiply all three of these together, we get 0 times xz, which is 2, over 1 minus the cosine of 0. Xy is also 0. So this is 1 minus 2 is, so this is negative of negative 1, and 1 minus cosine of 0 times 0 is just 1. And the negative of negative 1 is positive 1. All right. Let's keep going. Number 8. Find the equation for the tangent plane to this surface at the point 0, 0, 1. So the equation of a tangent plane looks like z equals a slope in the x direction plus a slope in the y direction plus an intercept. To find the slopes, we need the partial derivatives. And so we're going to take the derivative of z with respect to x and the derivative of z with respect to y. With respect to x, this is e to the x plus 2y times the derivative of x plus 2y, which is 1. With respect to y, it's e to the x plus 2y times the derivative of x plus 2y, which is 2, because now we're taking the derivative in the y direction. And at the point 0, 0, 1, this is e to the 0 times 1, which is 1. And this is e to the 0 times 2, and that's 2. And so now we know what the slopes are, 1 in the x direction and 2 in the y direction. But we still don't know what b is. So then we take the point 0, 0, 1 and plug this in. So now we're ready to look at the intercepts. Z equals x plus 2y plus b. 1 equals 0 plus 2 times 0 plus b. And so b is equal to 1. And so my final answer is x plus 2y plus 1. And that's A. By the way, once you got here, you could have eliminated x plus 2y plus 1 is b. Sorry, it has the 2y in it. Once you got the 1 and the 2, you could have eliminated all the other choices. You didn't need to do the work for the intercept, but this is how we do it. Okay. All right, let's move on to the free response questions. Let's compute the angle between R1 and R2. So the formula for the angle is that the cosine of the angle is equal to the dot product over the magnitudes. But if we work out the dot product is, in this case, 2 plus negative 1 plus negative 1. And the magnitudes, well, they're square root of 3 and square root of 6, but we're going to see that doesn't matter because this dot product is equal to 0. And since the dot product is equal to 0, then the angle has to equal 90 degrees. Or you could say pi over 2 radians. Whichever one you want. If we want to find the cross product, R1 cross R2, that's 1, 1, 1 crossed with 2, negative 1, negative 1. In the x position, we get negative 1 minus negative 1 cancels and we get 0. In the y position, we get negative 1 minus 2 would be negative 3, but we change the sign to positive 3. And the last coordinate, we get negative 1 minus 2, and that one's negative 3. And so that's your answer for part B. Suppose we knew the coordinates of V and we knew the value of the scalar projection of U onto V. Can we work backwards to determine the coordinates of U? And the answer is no. And here's an example why. Let's say this vector was our V. And this vector right here was the projection of U onto V. All that's telling me is that U starts on this line and it ends somewhere on this line. But that's all we know. You could go straight across, or it could have a very long downward trajectory, or a long upward trajectory. And all of these vectors would have the same projection. We know a little bit about the starting and the ending points, but we don't know enough to identify either the direction or the magnitude of U, and therefore we can't figure out what its coordinates are. So knowing the projection is not enough to work backwards and figure out what the original vector was. Okay? All right. Let's calculate the equation for this plane. We need two vectors, so let's use, I think in the solution key I used PR and QR. PR, that's the same thing as R minus P, and so that's -1, 0, 2. And QR is the same thing as R minus Q, and so that's 0, 2, 2. Their cross product is 0 minus 4, -2 minus 0, and -2 minus 0. And so this is our normal vector. Okay? And so the equation that we want is -4x plus 2y minus 2z is some constant. And we can check to make sure our work is correct because all three of these points should produce the same constant. When I plug in P, I get -4 times 1 minus 2 times 0 minus 2 times 0, so that's -4. When I plug in Q, I get 0 plus -4 plus 0, and that's -4. When I plug in R, I get 0 plus 0 minus 4, and that's also -4. And so our answer is -4x plus 2y minus 2z equals to -4. Okay? All right, let's look at number 12. We want to find the distance from the origin to the line 2 plus t, 8 minus t, and 2t. So this is a line that contains a point 280 and goes in the direction of the vector 1, -1, 2. Okay. Well, if I draw the vector from 0 to this point, and let's call that vector, in fact, I'll use a different color for that. V. Well, because V is this point minus the origin, the coordinates of V are also going to be 2, 8, and 0. Okay. So if we let P be the point 2, 8, 0, then vector V, which is O to P, which is P minus O, is the vector 2, 8, 0. And then the magnitude of V will be the square root of 4 plus 64 plus 0, which is the square root of 68. Okay? Then we can calculate the projection of OP onto the line. And we really only need the component projection. That's the dot product of this vector and the line vector. So it's 2, 8, 0 dot product with 1, negative 1, 2 divided by the magnitude of the line vector. So this dot product is 2 minus 8 is negative 6 plus 0 over square root of 1 plus 1 plus 4 over the square root of 6. Now the sign that I'm getting here, the reason why this is a negative sign, is because the projection is pointing in the opposite direction from the line vector 1, negative 1, 2. They're pointing in opposite directions, so we're getting a sign difference. But the actual length is just 6 over root 6. And so now we have this triangle here. This side is square root of 68. This side is 6 over root 6. And this side is the distance we want. We want the distance from the origin to this line. But we can use the Pythagorean theorem now. 6 over root 6 squared plus d squared equals square root of 68 squared. 6 over root 6 squared turns out to just be 6. Plus d squared is equal to 68. And so d squared is equal to 62. And so d is the square root of 62. All right. We're chugging along. 5 more. Number 13. Let's sketch this graph. So first thing I would try to do, once I have established that this is not a problem in which there's a missing variable or a missing square term. So this is not a paraboloid. This is not a cylinder. Let's try to find the intercepts. So we have intercepts for each axis. In the x-axis, we're looking at the equation x squared equals 36. And so x is equal to plus or minus 6. In the y direction, we're getting 9x squared is equal to 30, or 9y squared, equals 36. So y squared is equal to 4, and so y is equal to plus or minus 2. Along the z-axis, we have 4z squared equals to 36. So z squared is equal to 9, and so z is equal to plus or minus 3. So I have intercepts in every single axis in this case. In the x direction, they're 6 units out. In the y direction, they're only 2 units out. And in the z direction, they're 3 units out. And so what happens is that in the xy plane, we have 4 intercepts that connect all together. In the let's do the yz plane. In the yz plane, we have 4 intercepts that connect together. And then the xz plane, we have 4 intercepts that connect all together. And so what we've got is a shape that's called an ellipsoid. It's rounded at all of the ends. This doesn't look very rounded because I can't draw very well. But it has intercepts on all 3 sides. It never has curvature that curves away from the axis like a hyperboloid. And so this is an ellipsoid. If you download the answer key, you'll see a machine-generated version of this graph, and it's much nicer than what I can do by hand. All right. Number 14. We're going to try to calculate this limit. Well, this trig function here is complicated to work with, but we know that it's less than 1 and bigger than or equal to negative 1. So since negative 1 is less than or equal to sine of 1 over y squared is less than or equal to 1, then negative 2x plus 3y is less than or equal to 2x plus 3y times the sine of 1 over y squared is less than or equal to positive 2x plus 3y. And this is establishing a sandwich that we can use for the squeeze theorem. That since this is squeezed in between negative 1 and 1, this expression has to be squeezed in between negative 2x plus 3y and positive 2x plus 3y. And so the limit as xy approaches the origin of this slice of bread is smaller than the limit xy approaches the origin of this complicated sandwich filling. Let's write the function first, or the polynomial first, and then the trig function. And then it's less or equal to the limit as xy approaches 0, 0 of this other simple plain slice of bread. Well, this is a limit we can solve just by plugging in. When I plug in 0, 0, we get 2 times 0 plus 3 times 0 made negative, but that's still 0, is less or equal to this limit as xy approaches 0, 0 of 2x plus 3y times the sine of 1 over y squared. And then that's equal to, well, this is another limit we can solve by plugging in. 2 times 0 plus 3 times 0 is 0. So if this limit is both bigger than or equal to 0 and it's smaller than or equal to 0 at the same time, it must equal 0. Therefore, the limit as xy approaches 0, 0 of 2x plus 3y times the sine of 1 over y squared is exactly equal to 0. Has to be because it's sandwiched in between two zeros. All right. Okay, so we have a function here. We need to compute some partial derivatives here. So the partial derivative with respect to x, I have an x on one side and a y on the other. The x side gets the derivative. The other side doesn't change, so it's still y cubed. This is 5x and y squared. The derivative of 5x is 5, and nothing happens to the y squared. This is 4x to the third. All right, now the derivative with respect to y. This time the 3 is going to come down. We're going to get 3x squared y squared. Then the 2 is going to come down. This is going to be negative 10xy. And there is no y term in this. There is no y in this term, so the derivative is 0. All right. Let's use implicit differentiation to calculate this partial derivative. We saw an implicit differentiation problem in the multiple choice section. Here's an implicit differentiation problem in the free response section. The partial derivative in the order zx is the negative reciprocal of the partial derivatives. So we flip the order and change the sign. It turns out they're orthogonal to each other. Later on, we will see why that's true. But we have to move everything to the same side of the equation to use this formula. So my calculation, my formula, capital F, is yz plus x ln of y minus z squared. The derivative with respect to x, there is no x in this term. There is an x in this term. The derivative of x ln of y will be 1 ln of y. And there's no x in this term. The derivative with respect to z for this term is y. There is no z in this term, but this is going to be negative 2z. If I want to take the negative sign out of the bottom, I can. That gives me, instead of y minus 2z, it gives me 2z minus y. Just a slightly cleaner way of expressing the answer. Either of these are fine, though. This one or this one. Okay? All right, last one. Find the equation for the tangent plane to this graph at the point 1, 4, 2. So again, the equation of a tangent plane looks like z equals some slope times x plus some slope times y plus an intercept. To find the slopes, we need to know what the partial derivatives are. The partial derivative of this square root, this is the same thing as xy raised to the 1/2 power. So the derivative is 1/2 times xy to negative 1/2 times the derivative of what's inside the parentheses. Well, the derivative with respect to x of x times y is 1 times y. So this is just 1 times y. And then the same reasoning applies over here. The derivative with respect to y of x times y is x times 1. So we just get an x here. So at the point 1, 4, 2, this is 1/2 times 4 to negative 1/2 times 4, and that equals 1. But this is 1/2 times 4 to negative 1/2 times 1, and that's 1/4. And so z is equal to x plus 1/4 y plus b. So now to find the intercepts, we use this equation and we plug in the point. So that's z equals 2 is equal to 1 plus 1/4 times 4 plus b. Well, that's 2 is equal to 1 plus 1 plus b, and so b is equal to 0. Let's see. Well, b is equal to 0. We have our answer. Z is equal to x plus 1/4 y plus 0. And that's the equation of the tangent plane we needed. All right. I hope this helped. I'll hold office hours today at 10:30 to 11:20 a.m. and then tomorrow from 11 to 11:50 a.m. and then again later on from 2 until 3 p.m. These are not my usual office hours. These are makeup for last week when my power was out of the house. But this is a good time to hold some makeup just before the test. So make use of those office hours if you have any last minute questions. Y'all take care. I will see you Friday with new material. Good luck on the test on Wednesday.